All right, guys, let's talk about similarity transformations. Um, we're going to learn about what a similarity transformation is and kind of how to identify them and figure out things like scale factor and whatnot when things have been either reduced or enlarged, because that's basically what we've been talking about this whole chapter is things that are proportional to one another but not necessarily the same size. So we got some new vocabulary here. Here's some words we're going to have to define. Um, Dilation. You may have heard this term in biology, like when the pupil in your eye dilates, it gets bigger or smaller to allow in more or less light. And so a dilation in geometry is the same idea. We're taking a figure and we're scaling it up or down, or either making it larger or smaller. Center of dilation is a fixed point about which the dilation occurs. And I've got a sketch on the next slide that'll make that a little easier to understand. Scale factor of a dilation is the ratio of a given length in your image to the original. And that's like what we've been calculating when we've been talking about similar triangles, like K, our scale factor. How much bigger is this one than that one? And our two types of dilations are enlargements and reductions. And an enlargement is a dilation with a scale factor greater than 1. A reduction has a scale factor between 0 and 1, so some fraction to make it smaller. Okay, and here's a sketch that might make this a little easier to understand. Here we've got an enlargement. If we take triangle DEF and we scale it up about C, that'd be our center of dilation that we talked about. If we scale it up, we would end up with this triangle LMN, which is an enlargement. And turns out it's 3 times bigger than the original. So we would say that has a scale factor of 3. K equals 3 in this case. But in general, enlargements have scale factors that are greater than 1. And likewise, we could take here this blue quadrilateral is our original image. We could take that and scale it down. And again, we're scaling it down about some center of dilation C. And if we shrink this quadrilateral GHIJ down to WXYZ, then we've reduced it. That's a reduction. And this one is about a third the size of the original. So we would say K, or the scale factor, is 1/3. So when you're dealing with reductions, your scale factor is going to be between 0 and 1. Let's look at an example here. Here in this figure, going from figure A to figure B, what type of dilation do we have? Is this an enlargement or a reduction? So going from A to B, you can see that's getting smaller, so that's a reduction. And what's the scale factor? How would I figure out the scale factor? I could take the length of a side in A and compare it to the length of a side in B. Okay, and since this is a reduction, I know 0 is going to be less than K is going to be less than 1. I'm going to be dealing with some fraction, right? And let's look at this side and this side. In order to get that fraction, what I'm going to want to do is take the length of this side in figure B, 2, and put it over the corresponding length of the same side in figure A, 2 over 4 units, okay, which would simplify to 1/2. So we would say here the scale factor is 1/2. If I multiply everything in figure A by 1/2, I would get figure B. All right, let's take a look at another one like that. In this figure, going from figure A to figure B, is this an enlargement or a reduction? Here's A, here's B. You can see this one's getting bigger. So this is an enlargement, okay? Enlargement. And in that case, since it's an enlargement, my scale factor K is going to be greater than 1. So how would I figure that out? Could I take this side in figure B and compare it to the corresponding side in figure A, 3 over 1? So could I say that the scale factor is 3? All right, how about this one? Going from figure A to figure B, is that an enlargement or a reduction? Well, we got smaller going from A to B. So this is a reduction. Okay, and what's our scale factor going to be? I know that my scale factor is going to be between 0 and 1. I need some fraction to express what's happened to A to get to B. So I'm going to compare this side in B, 1, over its corresponding side in figure A, 3. So my scale factor is 1/3. All right, this one's a little trickier, but not too bad. We can handle this. Is the dilation from figure A to B an enlargement or a reduction? Well, you can see I'm getting smaller here as I go from A down to B. And so I'm going to be looking for that fractional scale factor. K is going to equal, could I compare this side on the smaller figure, 2, to its corresponding side on the larger figure, 3? Absolutely. So my scale factor here is 2/3. Okay, here's another one. A copy of a picture is 2.5 inches wide and 5 inches long. By what percent should the picture be enlarged so that its image is 2 times the original? Find the width and length of the enlarged picture. Okay, well, if it's going to be 2 times the original, doesn't that mean our scale factor K is 2? And if our picture is 2.5 inches wide by 5 inches long, it should look something like this. And if we want a copy that's twice as big, well, then I think we're going to end up with something like this. So 2.5 times 2 will give me 5 inches. Be now 5 inches wide. And the length of 5 inches, 5 times 2, would give me 10. So now it's going to be 10 inches long. So what's this question? By what percent should the picture be enlarged so that its image is 2 times the original? Well, don't forget, percent literally means per 100, right? So basically, how could I rewrite this scale factor as something with a denominator of 100, right? Isn't that the same as 200 over 100? Which is where we get 200%. Okay? So if you want to double the size of something, you're increasing it by 200%. Okay, let's see what Dave is up to this time. Dave wants to enlarge a photo he took that is 5 inches wide by 8 inches long. He wants to put the photo in a frame with a mat that is 300% of the original size. What will be the width and length of the enlarged picture? Okay, so if K here is 300%, and that literally means 300 over 100, 300 per 100, then we could simplify that and say our scale factor is 3. He wants the enlargement to be 3 times the original. So if our original was, let's say, 5 inches by 8 inches, then one that's 300% larger is going to be 3 times 5 gives me 15 inches, and 3 times 8 gives me 24 inches. Okay, so the enlarged picture is going to be 15 by 24. Okay, here's another one. Graph the original figure and its dilated image. Then verify that the dilation is a similarity transformation. So this part is interesting. Verify that it is a similarity transformation. We're going to look at what we have to do to determine that. Let's go ahead and graph this first, though. Point M is at -6, -3. So M is right here. And point N is at 6, -3. Okay, there's N. Yep. And point O is at negative 6, 6. Okay, so point O is going to be over here. All right, there's O, negative 6, 6. And as you can see, it looks like we have a triangle. Okay, so I'll just connect these guys here. And we've got an image, a dilation, or something that may be a dilation. We're going to have to confirm it. And that is DFG. So point D is at negative 2, negative 1. Okay, there's D. And point F is at 2, negative 1. So 2, negative 1. Here's F. And G is at negative 2, 2. Okay, so there's G. We're at negative 2, 2. Okay, as you can see, we got another triangle, but is it a similarity transformation? In other words, is this triangle similar to the original? How could we prove that? A couple of different ways we could do that. But probably the easiest, remember, when we're proving triangles similar, we have angle-angle. That was one method. We had side-angle-side, where we've got an included angle and the sides on either side of it are proportional to one another. And then we've got side, side, side. Now you could definitely go for side, side, side because we can find the lengths of all of these sides and set up those proportions. But you probably recognize that we'll have to use the distance formula for these two to get them into a ratio. So maybe side, angle, side would be easier. I'd love to use angle, angle. It's super easy when you can use it, but we really only know one angle here, and that is this 90-degree angle in each of these triangles. But we could use that and say, hold on, could we check side, angle, side? Compare this side to this side and see if it's the same ratio as this side to this side. So let's go ahead and compare and see if OM over GD equals MN over DF. If that's the case, then we'll have side, angle, side similarity. Let's try this. OM is how many units? You can look at your, since it's a vertical line, you can look at your Y values, negative 3 to positive 6. So you can see that that is 9. And then we can look at, do the same thing here, or you can just count these 1, 2, 3. GD is 3 units long, so 9 over 3 should equal, let's look at MN. You can just look at your X coordinates here. It looks like we go over 12 units. From negative 6 to positive 6, we went over 12 units. And that compares to, how long is DF? 1, 2, 3, 4. Okay. Is 9 over 3 equal to 12 over 4? You can probably recognize that these can both be reduced to 3 over 1 equals 3 over 1 here. Top and bottom are both divisible by 4. Good. So guess what? Those are proportional. The included angles are congruent. So we have side, angle, side similarity. Good. All right, let's try one more of those. Oh my goodness, what's that? What's this? Aha. That could come in handy. All right, let's do one more of these where we're going to graph here, set up a graph. It looks like we're going to want to be right about here. We're going to test and see if we've got a similarity transformation here. When we graph these, G is at 2, 1. So 2, 1, here's G. H is at 4, 1. So I'm going to go over 4 and up 1. There's H. Okay. I is at 2, 0. So there's I. And J is at 4, 0. Okay. I don't know about you, but I hope it's not a reduction, because we can't get much smaller than that. Q is at 4, 2, so I'm going to go over 4 and up 2. Here's point Q. That's going to be a little tricky. Q is at 4, 2. R is at 8, 2, so I'm going to go over 5, 6, 7, 8. R is at 8, 2. S is at 4, 0. So guess what? S is in the same spot as J. And T is at 8, 0. Okay. So now we can kind of picture what's going on here. We've got this rectangle right here. And then we've got this rectangle right here. Is this actually a similarity transformation? How would we figure that out? Well, we can see that all the angles in these two polygons are congruent. They're all 90-degree angles. So now we just got to see if the length to the width of this triangle, 2 over 1, okay, is 2 over 1 equal to the length to width of this triangle, 4 over 2. Does 2 over 1 equal 4 over 2? They both reduce to 2 over 1. So, yes. Okay. All right. Thanks for watching, guys. That is the lesson on similarity transformations. Good luck on the homework.